and we're going to talk a bit about our chapter 28. Okay, and so chapter 28 is going to be on magnetic fields, and magnetic forces. Okay, and so the big thing that we're gonna talk about is that we're gonna have that our magnetic fields are analogous to electric fields. So we're going to have a lot of similarities in terms of, how those are described and behave. And so what we get is that our magnetic fields are created by net magnetic moments of the fundamental particles that make up the matter of the magnet. And so like we had talked about before, it's a property or a characteristic of matter just like charge. So magnetic fields are created by net magnetic moments, or they're created by magnetic fields created by moving charged particles. Which is what we would call a current. Okay, so there's two ways in which we can produce a magnetic field. Either it's just the property of the matter, or it's essentially due to currents, are the two ways in which we can generate magnetic fields. And what we have is that magnetism has been known for like a fairly long time. Due to the discovery and the invention of the compass. Okay. Okay. And so when we talk about a compass, then really what we have is we have a magnet. So I have a set of bar magnets here. And then what we have here is this is a needle pivot. So it's a low friction pivot, so it should rotate fairly freely. And then if we put the compass, if we put the magnet and allow it to freely turn, then what will happen is it will go in and rotate until it points, a particular direction. And then what they discovered was that that direction was essentially, north. Okay. So if you allow it to freely turn, then it aligns itself always in the same direction. And so then this became the north-seeking pole of the magnet, because it points north. Okay, and then of course the other is our south pole. And as we probably already know, then when we have our magnets, they interact with one another such that opposites attract and likes repel. I can make that one turn by turning this one. So, like so. And so this is the, essentially the compass type of idea. And so a compass needle is just one of the, a bar magnet type of concept. Okay. Now one thing to take a look at is that if we take our magnet and we break it, you don't end up with a north pole and a south pole. You end up with two weaker magnets in each hand. Okay. And in fact, like I said, the fundamental smallest unit of magnetism is actually the magnetic dipole, which is a property of the particles that are fundamental. Like electrons don't have any smaller pieces or parts, and the electron itself has a magnetic moment, and it acts like a little magnetic dipole. Okay, so it itself acts like a little magnet. Okay, and that description is given in terms of the, magnetic dipole moment of the electron. Okay, and so what we'll have here so the smallest unit is the magnetic dipole. So unlike charge, where you have a positive and a negative, individually, with magnetism you always have the pair of poles always together. So that's described by our, magnetic dipole moment. I'll probably just call it the magnetic moment. So the electron has a magnetic moment. It acts like a magnetic dipole. Okay, so it acts like a little bar magnet. And there are no magnetic monopoles. Okay. And the poles are called, usually just call it north, but I like this idea of calling it a north-seeking pole, because it kind of describes how the compass needle behaved. And so I like that as a concept. I think it's pretty clear then. And it's how we defined it. We defined it based off the compass needle and then a south-seeking. Like we had with charges, then what you get is that, opposites attract and likes repel. Okay. And so we can do things similar to what we did with the electric field, is we can take little compasses and put them at various locations in space in order to map out the magnetic field. So, and what I have here is this is an oil. And suspended in the oil are little, iron filings, I guess is what you might call them. And so we can get them to distribute pretty evenly through there in the oil and be suspended, not just immediately fall down to the ground. And then we can take our bar magnet, and you'll notice that again the north pole is color-coded red. That's pretty common. It's the same way on most compass needles, as you have the red tipped end is the north seeking. And we put it into here, then these will act with the magnet and map out our magnetic field in the space surrounding the dipole. Okay, and so you can see that dipole pattern like we had with the electric field. Okay, and so I can pass that around, just don't drop the little block, and you might need to reshake it up. Good. So what we have is that's kind of the idea of mapping out the magnetic field. Just like putting the little test charges mapped out the electric field, putting little compass needles or little iron filing elements that behave like magnets because they have a magnetic moment, because it's a permanent magnet type of material. It's ferromagnetic. Then what you get is we can map out the magnetic field. Okay. And so then what we have is that the compass needle points in the direction at the magnetic field at that particular location points. And what we get is that there's one and only one magnetic field vector. Okay, and then from this we can infer the integral curves to this vector field. So at every point you have a vector defined, and so that makes what they call a vector field. And from these vectors we can go ahead and find the integral curves to that vector field, like you would do in a DE course, same kind of concept. And what you want is you want the curve such that that vector is tangent to the curve at each location. So likely you haven't had DE yet, but what I always tend to picture is if you go back to the chapter on projectile motion, then we had the ball moved in like a parabolic arc through space, and at all points along the path of motion, the velocity vector was tangent to the path. It's that kind of picture. So now what we have is we have the vectors first and we draw the line second. But we could go the other way just as the similar. So, and so then what we get I said, so from this we can infer the magnetic field lines. Such that the magnetic field vector is tangent to the magnetic field line. Thank you. At each point. And points in the direction of the magnetic field line. Which points the same way as the compass needle. Okay. And so this is essentially just like electric field lines, right? At every point, the electric field vector is tangent to the field line and points in the direction that the field line goes. It's the exact same thing. And then what we had was that the closer the magnetic field lines are to one another, the stronger the magnetic field at that particular point. So the greater the magnitude, okay. So again, the same as the electric field lines. They did the same thing, okay. And then what we have is that since since there's only one magnetic field vector at each point, then magnetic field lines can't cross, just like our electric field lines. And then the other thing that we have, now this will be different. Since there are no magnetic monopoles, since there aren't any magnetic quote-unquote charges, and the magnetic field lines, form closed loops. Or you can have them go out to or come in from infinity. Okay, so that was similar to the electric field. But since there were charges, which are monopoles for that field, then the electric field lines could begin on the positive charge and end on the negative charge. Okay, but in this case, since since the electron itself is a dipole, has a north and a south, then what you end up with is that this implies that the magnetic field lines form closed loops. Okay, so. Okay. So just as the electric field vector, determine the electric force on a charged particle. Then the magnetic field vector would determine the magnetic force on, and in this case it's on a moving charged particle. Okay, so that's going to be a little different. So there has to be motion on the charged particle in order to have our magnetic force type of idea. Okay.